We're going to get into our first panel, and this one's going to be moderated by Niki, who spoke a little earlier, and this one is called Taking Innovation to the Moon. Go ahead, Niki.
Welcome back. So we're going to do this in kind of like an informal way. It's not going to be a super formal panel. We're going to go down the table, and folks are going to present just a couple of charts, a handful of charts, just to set the stage. I do want to note, first of all, we should just stop and say, everyone here has been to the moon. Not them, but you know what I mean. Like, so.
Unfortunately.
To the moon. So we're learning a lot, and kind of what I wanted to do at this 5-year kind of milestone is say, take a moment to appreciate how much work has been done over the last 5 years to the point that not only did they get to the moon, those technologies have been matured, created in many cases, and matured in that 5 years and flown, which is huge. And they've been done a lot through tipping points, ACOs, SBIRs, and I want to say a lot of those require company IRAD. So these are true partnerships where we're in this together. So we wanted to start today off with some of the folks that have been to the moon, but for every one of them, and including them, I have lists of hardware, technology that we need to be testing that has been all the way through, high TRL, high fidelity ground testing and dirty TVACs, environmental testing, that are saying, where do I go now? How do I get a flight, right? How do I get, and so that's gonna be a lot of the discussion for the rest of the week as well. But we wanna talk here about lessons learned, what comes next, and all of that stuff. So with that said, and it will be mostly an informal kind of dialogue with questions back and forth after they do the brief presentations to set the stage. So I think, I haven't looked at the program. Are we starting with Thierry? Is that?
Charge, you decide.
I don't, who's next, Jamie? What's the first slide package? Right, is it just down? Okay. So it should be, yeah, there you go, perfect. We planned it just that way.
I think I'll stand, it's maybe just a little bit
okay,
easier.
Yeah.
All right. Good morning, I'm Thierry Klein. I'm president of Bell Labs Solutions Research at Nokia. As you may know, Bell Labs is the research part of Nokia, now part of Nokia, and this year we celebrate 100 years. So congratulations to LSIC on 5 years. I look forward to being back for 100 years.
It's kind of like dog years, though, right? I mean.
Thank you, Niki, for the invitation to be here today. I want to tell you a little bit about what we've been doing with deploying the first cellular network on the moon as part of the IM-2 mission. And you could really ask, like, why are we doing this? Why we're looking at cellular technologies? And we heard this morning from, I think from Clayton and from John about the airline industry. I would give you another analogy. Think about the telecom industry. Think about the communication capabilities we had 5 years ago, 10 years ago, 20 years ago, or at the time when we went to the moon in the 60s and early 70s. I would also ask you, think about COVID without your smartphone and your broadband access to the home. So think about how far we've come in the telecom industry and the communication capabilities that actually we take for granted today. How many of you can imagine your one day without your smartphone? All right. Now ask your kids.
Yeah, a day.
So we started on this journey. Bell Labs, we actually have been working on communication in space way back. Maybe not well known, but in 1962, we built the first communication satellite called Telstar. And on this particular journey, we started back in 2018, and we started thinking about the lunar economy and the great interest in going back to the moon, going to Mars. And all these pretty pictures you see of what a lunar economy looks like, you realize that none of that will happen without communication. We're talking about connecting not just astronauts, but also connecting rovers, machines, drilling equipment, transportation systems, and all of that requires a lot of communication. It's not just voice communication, but more and more it's data, imaging, sensor data, high-definition video, and all of that should be connecting multiple devices that need to be coordinated. So we started looking at that and saying, all of this is really great and it's fantastic and a lot of great technology needs to happen, for that lunar economy to be real, but none of it will happen if we don't connect these assets and we don't allow them to communicate and share data. So that sounds like a really interesting and really tough challenge. Bell Labs, we like tough challenges. But then we also said, like, well, we're the guys who built the advanced communication technologies for terrestrial applications. Why we're not looking to take those same technologies and bring them to space and bring them to the moon and eventually to Mars. So that's really where the journey started for us, and saying we should take the same technologies that connect billions of devices that all of you have in your pockets today. We should take those same technologies, bring them to the moon. But of course, a cellular network on the moon will look very different from a cellular network on Earth, even if it's built on the same standards-based technologies. So we started thinking, how do we reconceptualize what a cellular network looks like? How do we build it for the environment, for the mechanical stresses, the temperature, radiation, and all of that? And that led us to working with STMD and Tipping Point, and we were very fortunate to be awarded a Tipping Point in 2020 to build that network and deploy it on the moon as part of the IM-2 mission, working in partnership with Intuitive Machines, but also with Lunar Outpost for payloads that we connected. And so we launched at the end of February on IM-2. These are some pictures. You've seen some of these pictures. I think Clayton had a video from IM. Proud to say that our equipment is in the picture, and you typically find the Nokia network when you see these two semicircles in pictures that are in the, I circled them here in the blue circles, but you typically see two semicircles. That's our radiator. Underneath it, you see a gray rectangle. That's your entire cellular network in something a little bit bigger than a small pizza box. So we launched end of February. I claim we have the fastest network. My optical colleagues say you measure in bits per second. I claim the fastest network is measured in miles per hour. And then, as you know, what happened on the IM-2 landing, it landed off nominally, but we were still able to turn the network on. So after landing, after the Athena lander was in the crater, we still managed to get power for a short window of time, and we turned the network on. And that's a major, major proof point for us, saying we took cellular technology that we deploy on Earth, we reconceptualized what that network looked like from a swap perspective, from an autonomy perspective. It's an autonomous network that's self-deploying. We ruggedized it so that it would survive a launch, a landing, and it survived what I think is a rougher landing than anticipated. So it survived that. And when we were able to apply power to it, we could turn it on, and we could command it. We could send telemetry data to it. We get health data back, and we have evidence that it was a fully operational cellular network. We were supposed to connect two payloads. One was a rover from Lunar Outpost, and one was a hopper from Intuitive Machines. We have evidence that the equivalent of your smartphone was also operational after landing. Unfortunately, the network and the device were not operational at the same time, so we didn't make the first cell phone call, but we had an operational network, and that I think what Niki said earlier is really proof that we really advanced the TRL for cellular networks in space. I think we'll get to a lot of questions, and happy to talk more about it. I just want to leave you with a couple of thoughts. For us, coming from the telecom industry, the ecosystem and partnering with NASA, but also with other commercial companies, is just paramount to making this happen. I fundamentally believe that innovation is really at the intersection of disciplines, and innovation is at the intersection of industries. And us partnering with the space industry really unlocks a lot of the potential of the technologies. We also need to have a long-term vision, and we have to have strategic objectives. And then in Bell Labs, we like this concept of future back. So we imagine what the future would look like. We imagine the disruptive technologies we need, but then we need to start building a plan from here towards that goal. We cannot take just incremental steps and then figure out what the step is after we take the first step, and then figure out what the second step is. Yes, we need to take the incremental steps, but they have to build on the plan towards a bigger goal. Because otherwise, if you just take the first step, you might go in one direction and then you change course. So you have that ambition, you have that long-term plan, and then you incrementally take the steps towards it. you learn every step along the way. And a number of people say, well, the mission failed, you didn't make the cell phone call. For us, it's not a failure. The network worked, we learned a lot, we collected a lot of data, and we make progress, and next time we'll make that cell phone call. So I'll stop here and turn it over to my colleagues. Thank you.
Yeah. And real quick, before Stephen says, I just want to point out too, as important as the technologies are, having the, as nerdy as this sounds, acquisition methodologies, partnering mechanisms are so important. So real quickly, because it'll apply to a lot of people here, the IM2 mission that we're talking about, we should pause and say, I'm very proud we created that mission. That was not one of the planned CLIPS missions. It came about by the Prime payload. STMD went to SMD and said, hey, we would like to use your services to facilitate this, and put out that for Prime. IM came back and said, you know what, we'll do a whole mission for Prime and we'll sell the rest of the space. And then independently, totally different process and group, the tipping point calls were reviewed, and Nokia got selected. And then IM's deployable hopper got selected through the tipping points. And then when we looked at these, it was like, wow, this just makes sense, right? And so we inserted that whole Intuitive Machines 2 mission. So it can be done. Precedent has been set. And even then, it was like, at first, the procurement and legal folks were like, what? What have you done? But it all worked out, right? We set precedent doing that, so.
That Intuitive Machines, it's really proud that IM2 is only about less than 50% funded by CLIPS. We had STMD, we had corporate partners. It's a really good example of how an international, multi-organizational project can work and actually work on the moon.
Okay, so that, Stephen, yeah.
Great, happy to be here. I'm Steve Indyk. I'm Director of Space Systems at Honeybee Robotics. Historically, Honeybee's gotten some pretty good work on the surface of Mars. We have instruments on Spirit and Opportunity, Curiosity and Perseverance, as well as other landers that have been to the Red Planet. And part of that, we've done a lot of work with scientists for planetary science. And a lot of things they care about, as you might assume, is the planetary surfaces, the material, what you can analyze, potentially even what you can bring back. But what I'm going to be talking about today from the Honeybee side is our first hardware that landed on the lunar surface. So we've been talking, on our side, we've been talking about lunar sampling for many, many years. And I'm really happy and privileged to show off some of the cool videos and hardware that we did get there. So I'm going to talk about 3 specific instruments, right? We had 2 really great landings just, Jesus, like 2 months ago. It comes by so, time goes so quick here. But from the Honeybee side, we landed our TRIDENT drill as part of the Prime 1 package on the Intuitive lander. And then we landed our PlanetVac and Lister sampling systems on Firefly's Blue Ghost. So I'm going to talk a little bit about each one of those in a little more detail. And I'm going to make sure my slides are in the right order because somebody, me, didn't put them in the right order. So here's the very first slide. So here's our TRIDENT drill. This is a quick introduction to our TRIDENT drill. It's a 1 meter class drill, so it's a drill that can sample up to 1 meter deep. It's a very versatile drill. It can go through things like soft material, hard material, fragmented material. It's a rotary percussive drill, so think of like a jackhammer percusses to break up anything that's really hard. It's rotary to kind of scoop out and move any of the lighter or broken up material out of the borehole. As part of this, I'll also say a rotary percussive drill is the most versatile form of drilling for any of these unknown surfaces out there. If you want to go to Mercury, we haven't put anything on Mercury, hint, hint. A rotary percussive drill is probably the sort of sampling system you might want on an unknown surface. Interestingly enough, both Curiosity and Perseverance's drills on the end of the robotic arm also use the same mechanism, a rotary percussive drill. So a lot of the work that Honeybee's done for TRIDENT, this 1 meter class drill, has been done better part of 20 years. So you probably have seen some of these slides in the past. But it's taken a very long time to develop this technology to be ready to go on the lunar surface. One of the cool parts about TRIDENT is it's such a versatile and capable drill that we built 2 of them, one for Prime 1 and the other for Viper. We'll talk about Viper maybe another day.
Well, real quick, though, that is an important point. The reason Space Tech was flying, this is what I was saying about it's all one big story, right? The reason we were flying prime with the TRIDENT drill and the mass spec, that's the exact same drill and mass spec that was going on Viper. So it was raising the TRL of those technologies and testing it out, so that was intentional as well. Yeah.
Yes. And also on the Honeybee side, it's more efficient, more cost efficient to build multiple of one item as well. The scientists were very eager for data and results from this. Unfortunately, as we know, wrong order of slides, that's my fault again. Going back, I swear, spoiler alert. There we are. Unfortunately, as we know, the lander did not land nominally, but some of the success we can take away from our TRIDENT drill in operations on the lunar surface is we were able to operate the full suite of capabilities of the drill. Again, it's 3 actuators. It's a rotary percussive. It rotates, it percusses, and then it extends down the Z stage to create that 1 meter borehole. So in this case, we were able to operate all the capabilities that the drill has. Unfortunately, we just didn't get a lot of very interesting data from the exosphere of the lunar surface. So hopefully for next drill operations, we'll get some actual regolith. Moving ahead, the second one I'm going to talk about is our PlanetVac system. So PlanetVac, the short version here, it's a vacuum cleaner, except in cleaning. Instead of cleaning the lunar surface, you're trying to collect the material and you're trying to analyze it or look at it in some way. So this is just a high-level slide basically saying you take this cone, you put it on the lunar surface, you hit pneumatics on it. In a vacuum, pneumatics are very powerful. It disturbs a lot of the material that's there. In this case, we're talking about lunar regolith, primed to get kicked up. And then you pass that material down the path of least resistance. In this case, we're funneling that material down a tube into a captive area. This last part of the slide, category 3 there, is basically saying that PlanetVac is a very versatile system. So if you want to capture, you want to sieve, you want to take that material that you just collected and put it in somewhere else in an instrument or a method for sample return, you can do all of those things with a sample that you've collected. In this case, we were trying to just analyze some of the material or just collect it and then do a little coupon sample. Let's see if this will play. Here we go. So in this case, we're deploying the PlanetVac cone. You can see that white cone towards the right of it, and there we're firing the pneumatics. As I said, there's a lot of energy in those pneumatics, so you can see some of that debris getting kicked out from all around that cone. And then a lot of that material is also going into that cone and down the sampling path into a container, which I'll show you a picture of in a moment. Can I play that again? I always love that video. Oops, that's the container. But I'll also note here, maybe I wore out my welcome on trying to play it. Let's see, maybe that'll go again. Yeah, thank you.
Technology.
We can get things on the moon, but I can't figure out a clicker, can I? So anyways, in this you'll see there's such energy in those pneumatics that you'll see this little rock get kicked out as well, come right up and go back down. So again, pneumatics in a vacuum, very powerful. So where a lot of the material was thrown out in different directions, a lot of the material did make it into the sample cone collection system. So here is a before and an after sampling image of the inside container. On the left, you can see a clean, pristine sampling container. On the right, you can see a notable amount of the material that's towards the back end of the sampling container. You'll also note one of the experiments we included in here is a material coupon test. So at the back, you can see those little square coupons of different material to basically see, for future potential dust mitigation methods, what material the regolith seemed to stick to the most in this sort of processing method. Again, misplaced slides. Who did that? Moving on to our third and final piece of hardware that made it to the lunar surface, LSIC. LSIC is a heat flow probe measuring device. It's using a technology called coil line drilling. So instead of a rotary percussive drill, we're basically taking a rod, a curled rod, we're unfurling that curled rod into a linear tube, injecting pneumatics, again, high energy, below the surface to excavate and bore a deep hole. In this case, we were aiming for 3 meters of depth. This is a test video from our lab hardware. A lot of this work takes a lot of environmental testing. On the far right, you'll see the actual test chamber with lunar simulant, with a lunar simulant bin below it. On the left are, did that skip? Let me see. Yeah, here we go. Ooh, we're going to get a bigger video than I thought here. I tried to crop out the front of it. I guess I don't know how to make PowerPoint slides anymore. Anyways, it'll show the major components. I think in just about 30 seconds, it'll get through to the actual video clip that I wanted to show, but I won't replay this one because I don't think we need to see all this again and again. Anyways, what you see here is the actual Lister probe in animated form. There's the coil line tubing that I mentioned, and in a moment, you're going to see it unfurl and extend down, lowering the boom. At the end of the boom is a thermocouple at the end to take thermal measurements, as well as a gas nozzle. To do the excavation of the lunar material. And there you can see a deflector shield there being put on in the animation. And that is the full package of Lister. Yes, we land on the surface. Yay, really cool. And here, so now we see the actual simulant bin on the right. This is what I intended for everybody to see. Apologies for the preface. But in this case, you're going to start to see the boom lower. It's hard to see in the test bin, but you can see on the animation where that boom is in the process. And on the right, you'll see again, there's our application of the pneumatics in the lunar vacuum chamber. And then the dust kind of settles out. So that's basically how Lister bores a hole. One of the parts that I thought was very impressive about all the testing is it looked very similar to what data we actually got back in flight and what imagery we got back from flight. So let's see if this one's playing. Here we go. So you can see the Lister probe on the left as it's lowering down and starting to inject pneumatics into the surface. So in just a moment, you'll see a rather large burst of pneumatics come out, kicking up a lot of debris. It looks pretty similar to the test videos. It performed similar to the tests that we did in chambers here terrestrially. And that's just some of the sampling that we were able to do, or some of the borehole creation we were able to do there. I think with that, I'll pass the mic to the next side.
Two quick notes. One, I meant to ask earlier, and I know, Thierry, you did it when you talked about the tipping point, but if you could, when you're talking, please also talk about if there are any NASA partnerships or awards, what mechanisms that we're working together using, because that thing just helps everybody understand, like, because Honeybee has been through the whole spectrum of small business and grown and the whole work, so.
Yeah, and I can mention that real briefly. We've gotten a lot of SBIR work. We've gotten a lot of tech transfer work as well, tech flights, a whole slew of funding sources from different NASA programs to help develop this hardware to actually reaching the lunar surface. Again, TRIDENT has been in development in different forms for at least 20 years at this point. PlanetVac not far behind it, and similar to Lister. Lister's been in the works for at least 15 years as well. It's also interesting to say with PlanetVac, I forgot to mention it, it's such a versatile capability. It's also flying on the JAXA MMX mission, which is the Martian Moon Express, which will bring back the first Mars material from the Mars planetary system. It's a returning sample from Phobos, one of the moons of Mars.
It's a really, really good example of how it doesn't happen overnight, right? And that all these beautiful videos that you're seeing in missions is a culmination of that TRL maturation that's been happening for a couple decades, and the company growing as a result. And then the other point real quick before I turn over to the next speaker, Kristen John, I saw a tear glistening from her eye as she was watching the video. She is our technical integration lead for LSII, but she is also, and has been for a while, our dust mitigation lead. So Kristen, raise your hand. She was crying at your beautiful imagery. And that's a perfect lead in over here to Josh for EDS.
We're going to...
Oh, Tibor. Oh, shoot. Okay, yeah, that's right. He's online. Can Tibor hear us? And you're going to do the flipping?
Yes, I can.
Hi, Tibor. Yeah, you go ahead and introduce yourself, and we'll flip your charts.
Thank you so much for being there, at least virtually. So greetings from Luxembourg, from the Space Resources Week, actually, so that it's a very similar stuff. But it's really, really great to be there, at least virtually. So, and I would like to give just a very short introduction about our little company. It's a small company. Next slide, please. So we started as a Google Lunar X Prize team. It was just the crazy idea of me to set up a team in Hungary to go forward to the moon. And then to start with that, we founded Puli Space. Puli is a dog breed. It has a meaning, so that's the reason I tell you, if you don't know that. So if you have seen Mark Zuckerberg's dog, this is also a Puli, actually. So, but again, so Puli is not that young company, but we have been struggling to collect money, to raise money in Hungary for this crazy idea to send the Hungarian rover to the moon, but we survived. And then 2021, we got a Hero X award, actually. We call it NASA award, which led us to develop our instrument, the Puli Lunar Water Snooper. I will tell you a little bit more about that, which is on the moon right now. So, and this happened on IM-2 mission as well. So next slide, please. So we just got some the history was just we built a prototype, we tested them in lunar like environments, the moon-like environments, or rover, and we learned a lot about the lunar environment. And so that reason we started to check what can we measure actually, can we monitor the lunar environment. And this case we developed also the idea how can we look for water ice, and this is our next slide, which is our hopefully future. So we would like to be a prospecting company. About water ice, just to tell you something, one of the potential resources or potential useful resources on the moon is water ice, not only for giving actually so water for the potential astronauts, but it could be basic for rocket fuel, as you know. And I think that this is one of the most important things we want to get really a permanent presence on the moon with solid logistic systems, and we need some fuel depots actually. That's the reason so we just turned our attention also just to look at such things. Next slide, please. I don't go into details. We developed a neutron spectrometer. Neutron spectroscopy is one of the potential means to detect hydrogen in the upper 1 meter of the lunar surface. It is just the physics, cosmic ray are hitting the solar, the regolith and generate neutrons, and these neutrons can hit hydrogen atoms losing energy. So that means that if we have some neutron spectrometer showing low energy neutrons and a lot with high energy neutrons, and we can see an enhanced number of low energy neutrons, that means that there is probably a lot of hydrogen, which is probably water ice or something similar. So that means that neutron spectroscopy is a proven tool actually to look for that. Next slide, please. And just some examples, we have already some neutron spectrometer around the moon, and mostly on orbit. There was an attempt to get the neutron spectrometer on Peregrine 1. It unfortunately didn't succeed. So in that sense, our neutron spectrometer is actually the first Hungarian instrument on the moon, and I come to explain a little bit more about that. Next slide, please. So we have been we are using CMOS sensors to detect neutrons. Again, I don't want to go into much details, but it's actually the following stuff. So we use high quality scientific CMOS sensors to detect neutrons. Neutrons are neutral, as the name says. That means that we need something which helps us to detect them. So the idea is here just to get a very, very thin neutron sensitive layer on the CMOS sensor, which generates actually a reaction with the incoming neutron, and this reaction generates charged particles, which makes a flash on the CMOS sensor. So that means that we are counting flashes, or making images and then counting flashes on the neutron on the CMOS sensor. So this is the basic principle for our instrument. One CMOS sensor is just as it is, it's for the background. We can also measure actually the background radiation with that. The two other ones are identically prepared with this neutron sensitive layer, and we have a so-called gadolinium shield before of one of these prepared sensors, just to get rid of the slow energy neutrons. Gadolinium is just shielding against low energy neutrons. So that means that with these three sensors, we are able to get neutron spectroscopy. So we can go for the next slide, please. And this happened actually with Niki knows about that. It was Honey, I Shrunk the NASA payload. It was just a challenge by NASA and HeroX in 2020. First, it was an idea competition, if you like. So the goal was just to look for half a CubeSat range instruments which can do something useful on the moon. So this, we just picked up this idea what we had since 2018 or something like that on the shelves. Our colleague at David Luciani, he's the father of the idea. He's actually in his free time, or in his daytime job at CERN in the radiation to electronics group. So, and then we said, okay, this is something which we can try. We put together everything. We won the first prize in the idea stuff, and the second run, actually, a sequel, we could make a convincing project plan and budget. It was the request by Honey, Honey Shrunk the NASA payload, the sequel. Can we produce it in 1 year? And we did it. We produced in 1 year actually moon-ready instruments. We delivered it to the Jet Propulsion Laboratory in February, and so this is what came to the moon. That was also something very funny in that sense, because on the way to GPL, we talked to Intuitive Machines in Houston and showed them the instrument, and they said, oh, this is great, actually leave it here, because we have the hopper and we want to make some science and some search for water ice on the moon in the permanently shaded region. So this has happened, so we said, okay, we cannot leave it here because we have to give it to GPL, but we are happy, more than happy, just to deliver another one. And we made an agreement actually, and in half an hour or something like that with Trent Martin and his colleagues in Houston. So they say, okay, we provide the instrument. Intuitive takes it as a private payload. They don't charge for us, and we are looking for potential data buyer actually. So because in that sense it was privately financed stuff. So next slide, please. Okay, this is just what we can deliver if it goes on. So next slide, please. So we came to Intuitive Machines, and actually something, other funny thing happened. ESA just realized that we are flying with IM. It was also kind of good time, we have been on the right place at the right time, and we made the first data buy contract. As far as we know, this is the first ever deep space data cell contract with ESA, what we did. So when we flew on IM2, you know the fate of IM2, it's not the best, but actually, so we are, as Nokia, we are actually happy. The reason for that, we can show that we have been operating nominally during transit. We collected data from roughly halfway to the moon. We have been also operating on the lunar surface, and I think it's on the next image, next slide. Yeah, no, this is just a landing site. Can go further, please. Yeah, and this is the image what shows the lander actually lying on the crater. And since we got some data from the water snooper, we can just identify knowing the IMU data where we are, and you can see on the right picture actually this is green stuff. So we have been in the shadowed area. So this is what worked. So we got a short time. We have been operating nominally at -55, -60 temperature, which is out of the nominal operational temperature range. So we are, in that sense, happy. We have TRL 9. We got telemetry data from the surface of the moon. So this is good news for us. Next slide, please. You can see this is my laptop. It was roughly quarter to 11 in the night after the landing, so 4 hours after landing. And it was an emotional moment for me personally to see the first telemetry data coming from the moon, actually. So, and to finish it, the last slide I want to thank for all of the partners who made this possible. It was really a very good example on cooperation in a lot of ranges. Actually started with the Hero X project, where we got the help of GPL financing by that project. We have a very nice network in Hungary for design, manufacturing, everything, and testing with CERN as well. And the moon mission, as I mentioned, it was just together with Intuitive Machines. And I have to mention, we had a second snooper, water snooper on the Lunar Outpost map rover. Unfortunately, we didn't have the chance to see that working, but we think that it would have been the same. And again, this was the first deep space data buy thanks to Intuitive Machines, ESA, and our other partners. So this is what I just wanted to say. So it was a great journey for us, a very small company, and we are already working on the next mission to the moon.
Thank you, Tibor. Can you flip back to one of the images on IM2? I just want to pause here for a moment, because this is what happens. So this initiative, LSII and the consortium, I just want to pull on the kind of amazing things we can do when we work together and when we understand all the mechanisms out there. So Carol Galika back there, the Honey, I Shrunk the Payloads challenge that Tibor talked about, this really is the little payload that could. I mean, with very little funding and part of our cadre project with JPL, we started this prizes and challenges for any students here or any non-traditional space folks. Crowdsourcing prizes and challenges are amazing. I am dumbfounded regularly by the type of responses that we get, including this. So Tibor was one of the winners. That took him all the way through developing the hardware and doing the testing at JPL, as well as the mentoring, which really springboarded this business all the way to the moon and the data buy with ESA. So that is just really exciting and shows you how much we can do when we work together and really leverage the mechanisms that we have. So congratulations, Tibor, and I think that's it's very inspirational in itself.
Thank you so much also for your support, Niki, and then for all the stuff. It was really a great moment for us just to see that we are on the moon.
Okay, excellent. Thank you, Tibor. And up next, we're going to talk the electrodynamic dust shield, I believe. Go ahead, Joe. It's over to you.
Hello, my name is Dr. Joe Toth. I am co-PI for the EDS payload that was recently brought to the moon aboard Firefly's Blue Ghost Mission 1. So a little bit of where I came from. So I'm working at the NASA Kennedy Space Center in the Electrostatics and Surface Physics Laboratory. This laboratory was founded in the late 90s to solve electrostatics problems for the agency. A lot of that revolves around analyzing and characterizing charge generation, electrostatic charge on all kinds of different space materials. But we also do technology development using electrostatic principles. A lot of this technology development is related to understanding planetary science, but also, and that's where the EDS comes into play, is we develop technology for dust mitigation. So the EDS is the Electrodynamic Dust Shield. This shield is a relatively simple technology. All it really consists of is a set of electrodes that you can embed into pretty much any type of material. These electrodes are non-uniform in space, so when we apply a potential across them, there's a spatially changing electric field. And then we also apply an AC potential across them to make them non-uniform in time, and that lets us remove dust, as you can see in this video. Yep, there it goes. So real-time video, this is just a ground test right here, but we just apply voltage across the device, and it just blows the dust right off. So a little bit of the history of the EDS. So EDS has been around for a long time. believe it was the late 60s when the first concepts of the EDS came around. It was electric curtain used to basically clear dust off of surfaces, move dust around. But it wasn't until our laboratory picked up the technology in the early 2000s where we started applying this technology for space applications. Back then, I believe we were targeted towards developing the EDS for Mars. Then later in that same decade, we started testing this device on reduced gravity flights to understand how the EDS works in a reduced gravity environment. We tested it with actual lunar samples to make sure that it could work. And then there was a little bit of a gap until the 2020s. Early 2020s, we started flying the EDS on the MISSI missions to the space station. This let us actually put the EDS technology and all of its associated electronics out into space to understand how the EDS can survive in the hostile environment of space. Around that same time, we also were manifested onto the CLIPS 19D mission, which would become Firefly's Blue Ghost Mission 1. That was through the Game Changing Development Program. And then that's when we started pretty much working on the main project that I was kind of talking about earlier that we're going to be talking about. And then a few years later, we actually we were built onto the EagleCam payload. They had a bunch of cameras on their payload that they wanted us to put an EDS in front of in order to keep dust off of their camera lens. Unfortunately, there was not an opportunity for us to operate the EDS during EagleCam's mission. But then later, the next year, in 2025, earlier this year, Blue Ghost finally, they landed on the moon where we could actually demonstrate that technology. So, move here. So our payload is kind of shown in the top left there. We were stowed onto the fifth leg of the Firefly's Blue Ghost lander. And then eventually, when they landed on the moon, we were deployed directly onto the lunar surface. You can kind of see in that bottom left image there from the Scalps payload that was also on Firefly's lander. So we basically interfaced directly onto the surface. And then on the right here, in that big image there, those are the EDSs that we have aboard our payload. So on the left, we have a glass EDS. That's a set of electrodes embedded into a glass panel. On the right, we have a thermal radiator EDS, which is just an EDS that's placed underneath of a thermal radiating surface material. As you can see, this image here is taken right after we were deployed, and we are completely covered with dust, which was kind of surprising to me. Some of my colleagues might disagree with that, but for me, I was just shocked at how much dust we got just from simply deploying onto the lunar surface, which was good for us because we wanted to test how we can remove the dust, so getting dust on us was a good thing. And so I'll show you guys a video here. That is the real-time video of us removing dust. So we actually showed quite happily that we were able to remove dust off the surface. We ran a few more cycles, and eventually this is what the images we got to. So the glass EDS removed more than 95% of the dust off the surface. The thermal radiator didn't clear as much, but it still cleared fairly well, and we have reasons why that happened, but we were very happy with the demonstration of the EDS technology. So now that we've demonstrated the technology, the next steps is basically going to be trying to infuse this technology into future missions. The EDS is not a standalone technology. It basically exists so that way we can protect surfaces from dust. So we've developed EDSs for cameras, solar cells, thermal radiators. We make gasket EDSs, and we also develop technologies to convey dust using the EDS technology. So yeah, we work with a lot of different opportunities. We're constantly developing the EDS more and more for different programs and such. But yeah, the next major step is for anybody who wants to go to the moon, who's worried about dust. Well, we have the EDS ready to go.
Thank you, Joe. So real quick, though, I want to pause here because one thing here is different than the rest, right? Joe is from NASA. and this was a NASA payload, and I want to just talk about that after being the program director for the game-changing development, which is a lot of these projects, I guess all of these projects, these types of projects. I think there's a semantics issue or a way that we're communicating as well that we need to probably work on, and I would love some feedback. We're developing what I'm calling an infusion catalog for now. It's not the best name, but basically we have a lot of technologies and capabilities that we develop on the government side, and I think we probably could do a better job or need some feedback on how we talk about getting those published and tech transferred or open sourced. LSIC, for example, we've got databases there with test facilities and simulants and those sorts of things. But how do we connect those dots better? Because we are not developing this at NASA to really for us to fly it. We get the TRL up and we want to give it to you guys. And I think we could talk about how to make that process more efficient and effective. I can't remember which day. Is today the lightning talks, Jamie? Yes. So part of our lightning talks was trying to have some of these projects here and mainly get across, like, here is the person you can contact if you're interested in this. Same thing goes for like data buys and those sorts of things as well. But I think that's an area that we need to work on. I think we have a lot of technologies like this that we want to publish and tech transfer out to everyone here that can use it. That said, I'll hand over to our last speaker.
All right, morning folks. My name is Niharika, and I'm going to talk about Hopper. So I was the project manager and the lead engineer for Hopper in the last year, which was our rocket-powered drone payload that flew on our IM-2 lander this past February and landed on the moon in the South Pole in March. So this was proposed through a tipping point award in 2020, and we started working on it in 2021. And as we kind of mentioned earlier, IM-2 was largely STMD between both the Nokia experiment and Hopper. So we flew that this year. So a little bit of background for Hopper itself, and I once again really want to thank STMD and NASA for the work and allowing us to work on Hopper. Hopper we started work on in 2021. I also graduated in 2021 and immediately came to Intuitive Machines and started working on the software for Hopper. So as Hopper grew in the last 4 years, I also very much grew as an engineer. And so Hopper's been instrumental to not only my development in software, but my ability to then lead the project. So up until last year, we had a different project manager who got promoted, and I was called in to fill in the spot. And so through Hopper, and these are pictures of our TVAC test. So we completed a full vehicle TVAC test in late 2023. It's one of the last things I did as the software lead on the project. And it was when Hopper first came up all together, and we got to test the full end-to-end system. Both Nokia and Puli were involved. I have really great memories working with both your teams. For Nokia specifically, we went to Colorado for range testing. Really great memories working with all our partners involved. And here we did our TVAC test at Johnson Space Center. So that's that middle picture. And that was a week-long test we did. That was the first time that our team could see this really small vehicle. And you can't really tell the scale in that first picture. It has the IM-2 lander in the background. The Hopper comes about 3 feet tall, and so it's a very small vehicle doing very powerful science experiments. So I got the pleasure of taking Hopper from last year all the way to mission this year. So these are a couple pictures that we took in transit from Earth to the moon, the first one being soon after launch vehicle separation, and you can see Hopper glowing gold in the bottom right corner there. Soon after we separated from the Falcon 9, we completed a transit checkout with Hopper, so that night of. Unfortunately, all Hopper shifts ended up being very late at night. I'm sure that helped for some of our payload customers. They actually got to do day shifts instead. But we completed a full transit checkout where we checked out almost every sensor and payload on board Hopper. So both the DLR radiometer and the Puli space water snooper were checked out. The Nokia radio on board Hopper was also powered up, and we saw a nominal power draw, though it was not connected to the BTS to see connectivity at the time. But that was the first time that a group of, for the most part, almost every lead on Hopper was under the age of 30. And so we got to take a big risk on Hopper through STMD to build this vehicle, and with relatively young and inexperienced engineers, and got to fly it in space, and that's the first time we powered it up. Between Earth and the Moon, we completed a series of thermal checks just to make sure Hopper was still happy. We worked through small issues with getting telemetry back to our payload customer. But by the time we got to the Moon, middle picture there, we got health data from our payloads down to our customers, and we checked out our entire system. The last picture is not long before our landing. Just another picture of Hopper with a nice long shadow on the lunar surface. So Nova-C landed in the south pole of the Moon. It is IM-2 Athena is the lander. It's landed the furthest south on the Moon as of right now, and though it did not land softly, as mentioned today, it did not land upright, we still completed hours of operations, not just on the lander, but on Hopper as well. So, mentioned before, we turned on the Nokia radio, and we saw a good current draw, though we didn't power it up with the BTS. We powered up the water snooper as well, and were able to get health telemetry down to our payload customers. We really matured the TRL on various components on Hopper, including the laser, including our nav sensors, payloads. So though we didn't complete a full mission hop, so the ideal was to complete one demonstration hop off of Nova-C onto the surface, we didn't complete that. We were able to mature a lot of technologies through Hopper, not just our own systems, but for our various partners and payload customers as well. So this was a brief summary of all the goals we did have with Hopper had Nova-C landed upright, primarily being an extreme mobility demonstration mission to prove out technology that would allow us to access areas on the Moon that rovers would not be able to easily access, such as permanently shadowed regions and craters or tops of hills. That was a major component. That was our actual proposal to STMD, was our extreme mobility demonstration. Permanently shadowed region would be our fourth hop on the surface. We would have jumped into a crater, and the fifth hop would have been an autonomous hop back out of the crater to prove out the areas. Part of the extreme mobility is proving out areas that rovers can't get to at all, and may be unsafe for humans to get to until they're explored, at least initially. So hoppers would be able to open up the avenue for not just permanently shadowed regions, but things like lava tubes to allow for a precursor mission demonstration before humans would be able to access them. Nokia, though the Lunar Outpost rover was the primary host for their experiment, Hopper did have a UE involved as well. We would have been able to test lack of line of sight tests when we were in the crater. We had 2 cameras on board. We were going to get some of the most high-res close-up imagery of the South Pole, and then the water snooper's been mentioned, and we also had DLRs, the German Space Agency's radiometer, involved. So that long list of complex science and mission tasks really lent itself to building, having an STMD tipping point partnership. So all of those tasks are really high risk. They're low-level TRL. They're things that we haven't flown before. But they were things that we want to fly in the future, not just on hoppers, but through other missions as well. And so STMD was able to really help us define a mission goal, not specifically prioritizing things that NASA and other agencies will want in the future, such as the PSR. We also got testing support. We mentioned testing at JSC earlier. That was our TVAC testing. STMD was able to help facilitate that. And during our mission itself, we had engineers from NASA on board in our mission control room to help support the mission. So they were on console next to our mission directors and would be able to provide real-time explanation or priority support. On the flip side, as we talked about the risk aspect of this, STMD really supported in building up giving us a quick way to test and fail. Fly fast and test and fail fast. That's a motto that's going around in new space corporations in general. And with Hopper being such a high-risk mission, something that's never flown before with technologies that are almost have never flown before, almost dreamlike, we were able to grow a platform that we can sell further. We built it, and we've matured a lot of TRL through this STMD tipping point, and then we can build further ones through this knowledge that we know our system works. So that's allowing us to go through STMD first, and doing a NASA partnership really facilitated this. So.
Okay, and so, oops, is it on? Hello, hello. Is it, no? Okay, there it goes, okay. So I did want to say, does anybody here remember those credit card commercials where it was like a mom and a daughter go to New York City and they see Broadway shows and go shopping, spend all this money, and at the very end, and they show them like hugging, and then it says priceless, right? So I'll just say this is, to me, priceless. And there's so many things that we get from this kind of work, and so you just proved it right there with the skill sets. It may not be quantitative, right, but the experience and then having that team of folks of getting hands-on and ops experience and developing brand new technologies all within a few years and sending them to the moon is huge for both, you know, us personally, but also for our country and for the world, for getting to where we need to go. So congratulations on that. And I think we should share those things a lot more, because when you don't do them, none of this is possible when you don't grow those skill sets and along with the technologies. So skill sets, technologies, acquisition methods, and partnerships. Those are the 3 key points. Okay, so we have, let's see, 15 minutes, Jamie, right? And everybody's hungry, but we did get a lot of questions, and I was trying to kind of synthesize, because we have a lot of themes here. So let's see, I've got one. I'm going to kind of try to synthesize several different things that came up. So it is often said that a key role of the government is to provide the strategy and the stability to do the things that aren't yet profitable for industry and/or are common needs or challenges that multiple stakeholders need to be addressed to be successful. So in this vein, that would include things like, you know, test facilities. Many of you talked about the subject matter expertise, R&D, and publishing results from things like EDS, the different acquisition methodologies, but also just like the utilities and having interoperable systems. You know, interoperability comes up a lot as well. I've been kind of playing around with calling this something like community-driven IRAD, where NASA can help offset the cost of your IRAD that you're putting in. So in that vein, are there utilities or interoperable systems, GFE, GSE, or other infrastructure elements that would be most ideal for the government to establish? And if so, do you talk as a community to kind of identify what would be most helpful?
You want me to start?
Yeah, have at it.
All right. So I can start a little bit by, when you talk about utilities and infrastructure, one of the things that we were involved with last year was the Lunar 10 challenge from DARPA. And I think that was a very good example of painting a picture of something that would be needed in the future for lunar economy, but then bringing together multiple companies across multiple sectors, because it's not just one piece of infrastructure that you need, it's understanding how the different pieces of infrastructure work together. And for us, coming from the communication side, it was, on one side, we were getting requirements from some of the other companies that were there, and I think you guys from Honeybee were there as well, getting requirements on the communication infrastructure. So we know the technology, but then the question is, what coverage area do you need? What throughput do you need to provide on this? So getting that requirement in, but on the other side, we were putting requirements on other companies that were part of the effort, for example, from power, from construction, and so forth. So it was really that multi-sector infrastructure. And I think that's one thing that the government can certainly do, articulate the the long-term vision, and then bring the companies together that need to work together. It's not just one piece of infrastructure, but it all has to fit together. So I think that was that would be very helpful to understand how all the pieces fit together.
Yeah, Luna 10 is a great example, and I did want to point out Daniel here, if you can raise your hand. How many people here are familiar with Logic, the consortium interoperability? Yay, fantastic. So that chicken and egg kind of story, COM, power, all the PNT stuff, that comes up a lot, and that's with DARPA. So if you don't know about it, reach out to this guy right here, and he'll get you connected. Anyone else on that question?
I think I already mentioned testing in my slides. I think that's a big component. You guys have the facilities already in place, and I know there's more getting built up that make it hard, these type of facilities, especially the ones that are big enough for spacecrafts, even the size of Hopper, are hard for corporations to make on their own. So having that kind of partnership with the government really helps.
Excellent. Okay. Next question. What is the one thing that you would change or lesson learned from your flight that others should be cognizant of? Just one, though.
I can start there. Scalability. So I mentioned Hopper was a small vehicle. It's about 3 feet tall, about 2 feet wide at the landing gear. That you want to be able to scale that up for longer missions. Hopper was built around a 5-hop plan with about 700 meter of range. But when you want to do longer missions, maybe you want to stay in the PSR longer, or you want to reach a hill or a deeper crater, you need to be able to scale your vehicles up. So keeping that in mind as you design your vehicle early on, keeping that in mind as you size your components is a big engineering design choice.
I would advocate for testing whatever system you're planning on providing for any of these surfaces, these environments. Testing pays off tenfold. It's a very expensive process, but it really troubleshoots and makes sure that your system is as bulletproof as possible.
Yeah, I would add definitely test, and I would say be paranoid. Be paranoid about everything that can go wrong, that doesn't go wrong in the lab, but just keep testing and keep thinking about the contingency scenarios. And for us, I think we'd done some of that, but we didn't really appreciate until after landing how much we needed that, because we got the call that said, there's an issue, power is a constraint. What is the minimum amount of power you need for a minimum amount of time so you can still achieve some of your objectives and you can turn that network on? And we could answer that question very quickly because we had done those scenarios in the lab. We measured exactly how quickly we could turn the network on, what's the exact amount of power we needed. So think about not just the sunny day scenarios, because those are easy, but think about the things that could go wrong and how you react to all the different contingencies. And probably the one that will happen is not the one you planned for, but at least you have a lot of data from your scenario planning and your contingencies.
For EDS, I think testing is very important, definitely. I think our biggest lesson learned, probably, overall, we need to make sure that we keep our actual objective in mind. For EDS, we relied heavily on making sure that we had great images and such. And we spent most of our development through the payload, making sure that we did all the testing. We went through all, TVAC, shock and vibe and everything. But I think we needed a lot more focus on making sure that, our images were focused well, that, we had redundancy in the lighting and such that we needed for our images. I think that's where we kind of really needed a little bit more focus.
4 words, another bumper sticker: test as you fly. And that is so critical. Okay, we've got lots of different questions that are, I'm going to try to synthesize them, that are related to, in general, what your next steps are, or do you plan to publish? How do you share your data or your lessons learned? Are there studies for how what you have learned could be incorporated into kind of the larger Artemis planning? And those sorts of things. Like, what are your general next steps, and how could people find out more of things that you're able to share? And Thierry, you've got the Artemis. Yep.
You want me to go? Okay. So a few things. In terms of next steps, we've announced last summer that we're working with Axiom Space to put cellular technology into their next-gen spacesuits, and we'll demonstrate cellular technology on the Artemis 3 mission. So that's a public announcement we've made. I think in general, in terms of next steps, we're looking to evolve the system that we flew on IM-2, looking to evolve that. You said it's a 4G system, so longer term, we're looking at how we evolve that to 5G. And I think we're just interested in partnering with anybody here or in the industry in general who thinks that they have a comms challenge and they need advanced comms. So we want to fly more missions. We want to partner with anybody and everybody in the US, certainly, but also globally. And you mentioned Artemis. We had also, a couple of years ago, we've done a study, and NASA had asked us what would it take to get 3G, whether it's 3GPP, whether it's 4G or 5G technology, ready for the Artemis timeframe. So we did a pretty comprehensive study on that from an architecture design across hardware, software, reliability, all the way from the connectivity to the application layer. And there's a public version of that report that's available. If you look for Nokia Bell Labs, a system engineering and integration study, that's quite comprehensive, and it also laid out the roadmap for how you go from here to 4G or 5G on an Artemis 5 mission, and what are the steps that we should take in between.
And by the way, the Artemis folks had come to us when they realized that was actually a huge risk, a huge gap. I think it was, don't quote me, number 2 or 3 on their risk list. And they came and said, thank goodness, STMD, that y'all had gotten this started in 2020. And again, that's another example of why you have to start that technology maturation if you want it there by the time you need it. Any others in terms of how you might share data or what your next steps are?
Yeah, we're always looking to fly our vehicles again, so we're actively working on proposals for Hopper and partnerships, both national and international. There's other NASA partnerships we're looking at too, PRISM proposals and things like that. So actively looking for a next Hopper.
Yeah, from this mission specifically, there are several NASA blog posts out that talk about it, but I think our next steps is going to be publishing our data, putting it out there for everyone to see, and show the results and such, so hopefully people have a good idea of what the EDS can do. More generally, we are currently working with a lot of partners, both internal NASA, a lot of external partners, to help infuse this technology into future missions and such. And so I think next steps, we're also looking to license this technology as well for any industrial partners who are interested in developing this further and making their own EDSs and such. That's our major next steps.
From the Honeybee side, if you're a fan of Lister, I've got great news for you. We're flying Lister again on, I believe it's Draper's lander in upcoming missions. We also have MMX, which has another PlanetVac system, so we'll see a few of the same sorts of hardware returning to the moon. I'm sure, as anybody up here has already said, and any of our commercial partners in the audience or in the community would also say everybody's always open to talking about what they're doing and how they can collaborate with other entities and effectively use the capabilities that we all have or derive new uses and applications for those capabilities. So I always say reach out to any of us up here, anybody in the audience. LSIC does a really good job compiling some test facility resources in the LSIC wiki, as well as entities that post in the LSIC forum and some of the lists in LSIC about what technologies they're working on, maturing, and trying to advance in general. So those are other great resources to reach out to those of us here who are trying to achieve these big, lofty goals.
Great. And one last question, if folks' stomachs aren't growling too loudly. I think this one's a perfect one to kind of end on. So a key aspect of all the different technologies that you've talked here and missions is that they are all core foundational infrastructure capabilities that you would need to operate on any surface. and also to create a burgeoning commercial lunar ecosystem on the moon. So given this, can you talk a little bit about if your technologies have extensibility to other locations, such as Mars potentially, and what you can learn on the moon from that would apply?
I mean, yeah, we definitely looked into what it would take to fly a hopper in a different body. It all comes down to propulsive system. So how much thrust do you need to get up in the air? So because the way we've developed hopper, as I mentioned scalability earlier, that was an early part of our design process. So while it would not be an identical hopper, we would be able to use many of the same GNC and software, many of the same components scaled up for a different planetary body.
For EDS,
Can you hear me?
Oh, Tibor?
Yeah, go ahead.
Go ahead,
Yeah,
Tibor.
can you hear me? Just a short notice. We are also working on our next missions, and regarding other celestial bodies, we have been already asked if we could use the Puli snooper on Mars as well, on potential helicopter missions. So we would be more than happy to make measurements on Mars as well.
Excellent. Thank you, Tibor. Go ahead, Joe.
Yeah, for EDS, I said it earlier, but originally the EDS was developed when we started looking for space applications it was developed for Mars. It works very well with Martian simulants in a Martian atmosphere. So we're pretty ready to be able to transition over to that. We're not currently actively working on that development, but it should be easy to transition over to that. And pretty much any planetary body now, demonstrating on the moon kind of shows us that it's a very successful technology that should work for any system.
Can you talk some about,
Yeah, from the Honeybee side, a lot of our capabilities are pretty versatile across different planetary surfaces. As I mentioned before, we've been on Mars. We have hardware that will be going to the Mars planetary system. Rotary percussive drills are very versatile. We're even flying one on APL's favorite flying mission, Dragonfly, right? We're providing the sampling system for that. Again, an unknown surface, very versatile capability to do very great sample acquisition, handling, and science. So a lot of the PlanetVac, Lister, again, it's kind of whatever environment you're trying to sample from or collect samples from. There's probably a solution in that trade space that could involve a PlanetVac, a Lister, or a rotary percussive drill.
So from a communication perspective, I would say the core technology that we would deploy on the lunar surface for communication on the surface is extensible to Mars as well. One of the things that we would need to redo is simulate the RF propagation environment, which was one of the things we were hoping to accomplish on the IM-2 mission, to take measurements and then calibrate the measurements against the simulation models. So that would definitely look to redo that for the Mars environment. The one big change from a communication perspective is when you look at how you connect Earth to the moon or Earth to Mars. Just the delay to Mars will completely force us to rethink the communication architecture and how do we handle that 15 to 20 minute one-way delay, which is going to the moon is already a long delay as far as we're concerned from a communication perspective, but going to Mars will be so much more challenging, and that might trigger us to think of completely different protocols as well as how we actually communicate and what is our expectation on Earth of when we get the data. So there's definitely no real-time robotic control from the moon back to Earth and even less from Mars back to Earth. So I think it's more the long haul that will be different versus the on-surface communication.
Yes, a true paradigm shift, and I think, we truly become Earth independent, and I think we have to practice that on the moon, So I do want to just take a moment and give everybody here a real round of applause. They've had no sleep for years. And they've been to the moon. So let's find more ways to get us all back there as soon as possible. Thank you so much. Everybody go grab a bite to eat.